Good morning to all. Today we are discussing about classification of clampers. In the last class, we studied about introduction of clampers. A clamper circuit can be defined as a circuit which can add a DC voltage to an AC waveform. Then the input signal can be shifted to either positive side or the negative side. That circuit were called as clamper circuit. Okay, today we discuss about the classification of the clampers. Okay, the clampers can be classified into two types. First one is the negative clamper and other one is the positive clamper. Again, the negative clamper can be classified into two types. First one is the biased negative clamper and other one is the unbiased negative clampers. Okay, and again the positive clamper circuit can be classified into two types. First one is the biased positive clamper and other one is the unbiased positive clampers. Okay, and now we discuss some important points about the capacitor. For example, here we are consider the one circuit. Okay, the circuit consisting of the voltage source, capacitor, and it have the resistor. Okay, and now our doubt is how much time is required the capacitor to store the maximum input voltage. Okay, we know that the voltage across the capacitor Vc of t equal to V of 1 minus e power of minus t by tau. This equation we are consider from the VW subject. Okay, so in this equation the time constant tau equal to RC. For example, here we are consider the resistor equal to 0. At the time constant tau equal to 0. Therefore, the voltage across the capacitor Vc of t equal to V of 1 minus e power of minus t by 0. Then we can get the voltage across the capacitor Vc of t equal to V. It means that, for example, in this circuit, the resistor equal to 0, then the time constant tau equal to 0. Therefore, the capacitor can store the voltage very quickly. Okay, and with respect to this equation, we are drawing this capacitor voltage waveform. Okay, for example, at t equal to 0 instant, we get the Vc of t equal to 0 volts. Okay, for example, at t equal to tau seconds, then we are get the voltage across the capacitor Vc of tau equal to V of 1 minus e power of minus tau by tau. Then we are get the Vc of tau equal to 0.637 volts. It means that at t equal to tau instant of time, the capacitor can store the 63.7% of from the input voltage. Okay, and similarly we are substituting at t equal to 5 tau seconds. At that time we are getting the Vc of 5 tau equal to V of 1 minus e power of minus 5. Then we are getting the 0.99. It means that the capacitor can store the maximum input voltage. It will require the practically 5 tau seconds. Okay, for example, we are consider the t equal to infinity. At that time we are getting the Vc of t equal to V volts, but practically the infinity voltage is not exist. Okay, so with respect to this explanation, we concluding that the capacitor can store the maximum input voltage. It will require the time equal to 5 tau seconds. Okay, and with respect to this equation, we are concluding some important points about the capacitor. For example, in the given circuit, the resistor equal to 0, then Vc of t equal to V volts. Therefore, the capacitor charges very quickly. Okay, for example, in this circuit, if we are increasing the resistor value or if we are increasing the capacitor value, then the time constant tau also increases. Therefore, at the time, the capacitor charges very slowly. Okay, and here we are assuming this voltage source is removed. It means that this voltage source is short circuited. At that time, this capacitor is acting as a voltage source and this capacitor is start to discharging. Okay, and now we are redraw the circuit with respect to this voltage source is short circuited. After redraw the circuit, okay, that circuit voltage source is short circuited, okay, and that circuit consisting only the resistor and the capacitor. Already the capacitor initially stores some voltage. At the time, this capacitor is acting as a voltage source and it will supply the current to this resistor. Okay, at the time this capacitor is start to discharging. Okay, and we know that the discharging of the capacitor vc of t equal to v of e power of minus t by tau, and here we are consider the tau equal to RC, and here this RC we are called as discharging time constant. Okay, and with respect to this equation we are draw the discharging of the capacitor. Okay, first of all initially at t equal to 0 instant, then the voltage across the capacitor Vc of t equal to V, and similarly we are substituting at t equal to tau seconds. At that time, the discharging of the capacitor Vc of tau equal to 36.7%. It means that at t equal to tau seconds, the capacitor have the 36.7% of voltage. And if you keep on increasing the time at t equal to 5 tau seconds, the capacitor totally discharges to 0 volts. Okay, now with respect to this explanation, we concluding that the capacitor charging and discharging is depending upon the time constant tau equal to RC. Okay, and here the capacitor discharging and charging action is helpful for understanding of the operation of the clamper circuit. Okay, now we discuss about negative clampers unbiased. Okay, the negative clamper circuit I show in figure. Okay, the circuit consisting the voltage source, capacitor and the diode, and the capacitor is connected in series with voltage source. Okay, and the diode is connected in parallel to this voltage source. Clear? And here we are applying the input voltage is as the square waveform or the sinusoidal waveform. Okay, and as per the analysis of the negative clamper circuit, we are applying either the square waveform or the sinusoidal waveform. Okay, and as per our better understanding purpose, first we are applying the square waveform as the input. Clear? And here in this circuit, the diode is considered as the ideal diode, and sometimes we are consider the diode is the practical diode. And the first we are assuming the diode is ideal. Okay, and again we are redraw the circuit. This is the capacitor, and here we are connecting the ideal diode, and here we are take the output. When we are analyzing the clamper circuit, always we are approaching the open circuit method. The open circuit method means this diode is open circuited and we are determining the anode voltage and cathode voltage. Based on this anode and cathode voltages, we are conclude this diode is forward biased or the reverse biased. Okay, for example here we are redraw the circuit. Okay, the diode is open circuited. For example, this diode is open circuited, then we are find out the anode and cathode voltages. Okay, for example here we are applying the input and we know that the voltage at the anode is V input and this cathode is grounded, then the V cathode voltage equal to 0 volts. Okay, and here we are assuming the first condition, VA is greater than VK. Okay, and here the VA means input voltage or not, therefore input voltage is greater than 0. So this is we are consider the first condition. If we are consider the input voltage is greater than 0 means the diode is in forward biased. Okay, at the time this diode is short circuited. Here we are applying the input voltage, and here we are connecting the capacitor, and here we are short circuited the diode. Okay, and here we are take the output. Now you can tell me what is the output voltage actually here, 0 volts or not. Okay, and here we are estimate the at that time what is the voltage across the capacitor. Okay, so we want to find out the voltage across the capacitor, therefore we can apply the KVL in this equation. Then we get the minus V in plus VC equal to 0, therefore the voltage across the capacitor VC equal to, we can getting the V in, therefore the V in equal, for example we are consider the positive half cycle. Okay, then we can getting the VM. Okay, and the other condition of the circuit is, for example, the input voltage is less than 0. At the time this diode is operated in the reverse bias condition, therefore the diode is off, therefore this diode is operated in the reverse bias condition. So here when the Vn is greater than 0, the diode is on, and this diode is operating in the forward bias condition. Okay, and coming to here, when the diode is a reverse bias condition, it can act as a open circuit, therefore here we are diode is open circuited, and now we are estimate the output voltage, V output voltage. For example, initially already the capacitor can store the voltage equal to how much actually here, Vm or not. Okay, and now we are estimating the output voltage and apply the KVL in this circuit. Okay, then we can getting minus V in plus Vc plus V out equal to 0. Therefore V out equal to, we are getting what now, V in minus Vc. Okay, therefore V in, already initially the capacitor can store the voltage equal to Vm, then we can substituting them minus Vm, therefore the voltage across the capacitor Vm, and with respect to this capacitor voltage we are getting the output voltage V out equal to V in minus Vm. Based on this equation we are draw the input and output waveforms of this negative clamper circuit. These are the input and output waveforms of the negative clamper circuit. Okay, and here we are applying the square waveform input. This square waveform during the 0 to t by 2 instant it have the positive voltage Vm, and during the t by 2 to t seconds it have the negative voltage minus Vm. We know that the voltage across the output side V out equal to, we will get the equation is V in minus Vm. Okay, and as per our convenient point of view we are substituting the V in equal to Vm. At the time we will get the V out equal to Vm minus Vm equal to 0 volts. Therefore during the 0 to t by 2 instant this output signal equal to 0, and similarly V in equal to minus Vm, we can getting output voltage V out equal to, we will get minus Vm, and minus Vm equal to, we are getting minus 2 Vm. During the t by 2 to t instant the output voltage equal to minus 2 Vm. Similarly during the t to 3 by 2 seconds the input signal have the Vm voltage, then again we are getting the 0 volts, and during the 3t by 2 into 2t seconds the input voltage is minus Vm, and again the output voltage equal to minus 2 Vm. It means that now you can observe in the input and output waveforms. Okay, the input signal is clamped to negative side. That is the reason this circuit we are called as negative clamper. And in this waveform, we need to estimating the DC voltage, that is V out average equal to 1 by T integration of T by 2 into T minus 2Vm into dt, that is equal to 1 by T into minus 2Vm. We can integrate in this, we can get in T, and upper limit is T and lower limit is T by 2. Now we can substitute in this, we are getting the V out average or VDC voltage equal to minus Vm. It means that the DC voltage of this clamper circuit is minus Vm. Okay, with respect to that, we are estimate the DC voltage of the this output signal. Okay, and in the another way also we need to redraw the this output waveforms. Okay, another method is first condition. When the input voltage is greater than 0, the diode is forward biased. Okay, therefore the diode is acting as on. Okay, at that time the output voltage of the circuit V out equal to 0 volts. And coming to the second condition, when the input voltage is less than 0, at that time the diode is off and it is operating in the reverse bias condition. At that time we are redraw the circuit. Actually here this is for the V in, and here we have the capacitor, and here we are connecting the diode is open circuited, and now we are estimating the V output voltage. Okay, now we can apply the KVL in this loop, then we can getting V out equal to minus, okay, then we can getting minus V in plus Vc plus V out equal to 0. Okay, therefore V out equal to, we are getting the V in minus Vc. We know that initially at the input voltage is positive side. At that time the diode is forward biased. At that time we can getting the capacitor voltage Vc equal to minus V. Then we can substitute here minus Vm. Therefore V out equal to V in minus Vm. Okay, and again we can substitute V input equal to Vm volts. Then again we can getting output equal to 0 volts, and we can substitute V in equal to minus Vm volts, and again we are getting the output voltage equal to minus 2Vm. So in this way the input signal is clamped to the negative side. Okay, and next we discuss the if the diode is the practical diode. This is also called as a constant voltage drop model. Okay, so in this constant voltage drop model, the diode is on. Okay, therefore the diode is replaced by a constant voltage source. Okay, the cut-in voltage of the diode is 0.7 volts, and for example the diode is off. Okay, the diode is open circuited. Clear? And with respect to this practical diode, again we are analysis the negative clamper circuit. Okay, and the first condition of the negative clamper circuit is the input voltage Vin is greater than 0. At the time the diode is on, and it is operated in the forward bias condition. Again we are redraw the circuit. Okay, that is here we are consider the input voltage, and here we have the capacitor, and in the practical diode point of view, replace the diode by the voltage source. Here cut-in voltage equal to 0.7 volts, and here we are consider the output. Okay, here the output voltage equal to 0.7 volts. Clear? And now we can estimate them how much voltage across the this capacitor we see. Therefore apply the KVL in this loop, then we are get them minus V in plus Vc plus V out equal to 0. Okay, therefore the voltage across the capacitor Vc equal to, we are get them V in minus V out. Okay, and here we are consider them V in minus V out equal to 0.7 volts. Therefore, the VC equal to, we are consider the V in minus 0.7 volts. And for example, as per our convenient point of view, this is the positive half cycle. In this positive half cycle, the input signal voltage is equal to Vm. Therefore, we are getting Vm minus 0.7 volts. Therefore, the voltage across the capacitor Vc equal to Vm minus 0.7 volts. Okay. And during the negative half cycle, that is V in less than 0, at the time the diode is off, and it is operating in the reverse bias condition. Okay, in the constant voltage drop model, the diode is reverse bias condition, it can acting as an open circuit. Therefore, again we are redraw the negative clamper circuit. Okay, and this is we are consider the V input, and here we are connecting the capacitor, and initially the capacitor can store the Vm minus 0.7 volts, and here the diode is open circuited, and here we are connecting the output terminal. Therefore, here we are take the output. Okay, and now we can estimate them how much voltage across them this output terminal. Okay, therefore we can apply the KVL in this loop. Then we are get the minus V in plus Vc plus V out equal to 0 volts. Okay, so here we require the output voltage or not. Therefore, V output voltage equal to V in minus Vc. Okay, and already we are estimating the V in minus Vc equal to what? Actually, Vm minus 0.7 volts or not. Therefore, Vm minus 0.7 volts. Therefore, we are getting the V in minus Vm plus 0.7 volts. Therefore, in the constant voltage drop model, the output of the negative clamper circuit V out equal to 0.7 volts minus Vm plus V in. Okay, so based on this equation, we are drawing the input and output waveforms. Okay, these are the input and output waveforms of the negative clamper circuit. Okay, now we can observing the input signal. The input signal during the 0 to t by 2 second, it have the 5 volts input, and during the t by 2 to t seconds, it have the minus 5 volts input. Okay, and we know that the output voltage of the capacitor V out equal to, we are getting 0.7 volts minus Vm plus Vin. This is the output voltage of the negative clamper circuit. Okay, now we can substitute the Vm equal to 5 volts and Vn also we can consider 5 volts. Then we can getting V out equal to how much actually here? 0.7 volts. But now this is compared with the ideal diode. In this ideal diode, we can getting V out equal to 0 volts. Okay, but coming to the practical diode, the cut-in voltage of the practical diode is 0.7 volts. Therefore, we can get the V out equal to 0.7 volts. Okay, similarly, during the negative half cycle, the input voltage is minus Vm. Therefore, we are getting V out equal to 0.7 minus 2 into Vm. For example, in this input signal, Vm equal to 5 volts. Okay, then we can getting them 0.7 minus 10, we can getting them 9.3 volts. Okay, therefore, with respect to these signals, we are draw the output waveform. Okay, during the 0 to t by 2 seconds, okay, the output of the negative clamper circuit is 0.7 volts, and during the t by 2 to t seconds, okay, the output of the negative clamper is minus 9.3 volts, and again during the t to 3t by 2 seconds, again the input of this negative clamper is 5 volts. Okay, therefore the output voltage is equal to 0.7 volts, and similarly we are getting them minus 9.3 volts. So in this way we are draw the output waveforms of the negative clamper circuit. Okay, thank you.